All right, welcome to lecture 4 on the definition of topology. So here it is. Oh, I said I should read the introduction to chapters 3 of Manetti on page 39. Let me do that before I forget. So Manetti tells us here that, some requirements we'd like for a topology are any point in X is an interior point of X. If X is an interior point of A, then X is an A. If X is an interior point of A and A is a subset of B, then X is an interior point of B. If X is an interior point of both A and B, then it must be an interior point of the intersection. And if A up or not, let's see, A degree denotes the set of interior points of A, then any point in the interior of A is an interior point of A. That's kind of a word salad right there. Exterior points of a subset are those that are interior to the complementary sets, and boundary points are neither interior nor exterior points. And then he claims the 5 conditions above can be adopted as axiomatic definition of a topological structure. And man, I wonder if I assigned that. I probably should have, but oh well. So that's interesting. I think there's actually, I don't know, who knows how many there. There are a number of different ways you could define a topology, but I will go with the standard one here, as does Manetti. And so to define a topology on a space, all right, is to define which sets are open. All right, so to start with, we just simply declare the collection of open sets. So let's do it. Definition: a topology on X is a family. I'll call it, I'm going to call that tau of subsets of X, all right? But really it's a script T, but I'm going to say tau so it's easier to, you can hear me say tau, right? So elements of a topological space are typically called points, all right? So that's something. And so the family of subsets of X are called, by definition, open sets, and they have to satisfy the following requirements. Axiom 1, the empty set and the whole set are in tau. In other words, the empty set and the whole set are open. The union of open sets is open. In other words, if I take a collection of sets in tau and I union them, I get another set in tau, all right? The intersection of open sets is open. Here we've just stated it for 2. That's convenient because you want the definition to be minimal. That way when you have to check if something's a topology, you only have to check if the intersection of 2 things are, again, in the topology. So what does this mean? This means if we pick A and B in tau, that implies that A intersect B is also in tau, okay? And a space paired with a topology forms a topological space. All right, so one thing I should mention, axiom 3 could be replaced with, instead of 2, like a bunch. All right, the intersection of finitely many open sets is open in a topological space. Here's the proof. So if we take open sets A1 through AN, for n a natural number, then of course we have that A1 intersect A2 is in the topology by axiom 3. And if we take the intersection of 3 things, we can look at it as the intersection of these 2 things with that third thing. So in other words, it's still the intersection of 2 sets. That's open, therefore, by definition, by axiom 3, the intersection of all 3 is open, right? It's in the topology. And then inductively, suppose that n minus 1 intersected is in the topology, and consider the n-fold intersection of open sets. But that's, the intersection of the first n minus 1 with the nth one, which again is open, intersect, open. By the induction hypothesis in axiom 3, we get that the intersection of n-fold open sets is again open. So we could just as well have replaced the 2 things in the definition with n things, but there it is. Example 1. So here's a topology you can always give. All right, so, well, that's not true. Sometimes you have a space which already, for whatever reason, is given a topology, right? And if that was the case, then you would have to say that it's too late to topologize. Too late. That's right, Audric. I said it. Anyways, so sorry. Let X be a set, then tau containing just the empty set and the whole space defines a topology called the trivial topology. This is a very silly topology, but there it is. There's also the opposite end of the spectrum. You could take the power set, right, to be the topology. What this is called is called the discrete topology. Literally every subset of X is open in the discrete topology. It's like, what's open in the discrete topology? Well, is it a subset of the space? Yep. Oh, it's open. End of story, right? So, but already, examples 1 and 2, right, show what? They show that there are more than one topologies. It grammatically seems wrong. Anyway, there is more than one topology for a given space, all right, a given non-empty space. I'll let you decide, excuse me, whether or not there's more than one topology for the empty set. Let's see here. You guys can argue about it in the comments if you want. Example 2. Suppose we have this 3-point space. 3-point spaces are great for homework and tests. So ABC. Then a topology we could give would be empty set, whole set, set containing AB, set containing B, set containing BC. So this topology has 1, 2, 3, 4, 5 sets in it. All right. And you can run through the list of axioms. It's got the whole thing. It's got the empty set, right? You take the union of any two of these guys, you get back another one of them, right? Like the union of the two-point sets just gives you back the whole thing. If you take AB union B, just get AB again. If you take AB intersect, I was like, why did I just do the same thing? Oh, this intersection. AB intersect B, just get B. AB intersect BC gives you B, so it's closed under unions and intersections. You don't have to worry about infinite unions or intersections because this is a finite example. So anyway, you can verify that tau here is in fact a topology. And you can contrast that with the discrete topology. The discrete topology here has the empty set, the whole set, the singleton A, the singleton B, the singleton C, set containing AB, set containing AC, set containing BC. There are 1, 2, 3, 4, 5, 6, 7, 8. That is not an accident. The power set of a finite set, the number of things in it is 2 to the finite number, which we're talking about here. 2 to the third is 8. Okay, not an accident. And so in this context, the initial topology we were talking about here, this one, it's a subset of the power set. And what this means is that the topology tau is coarser than the discrete topology, whereas the discrete topology is finer than the given topology here, right? So this is language we can use to compare topologies, provided that one topology is contained in the other, or vice versa, right? I suppose it's possible to have topologies on a space which you can't compare. I feel like that might be true. Huh. Actually, I'm not sure. Right offhand. See, this is one of the unfortunate things about not having a class. Like, I can sit here and think about it myself, but it's no fun. If I had students in a board, we could think about it, but sorry. You can answer in the comments. Is it the case that any two topologies can be compared? Or do there exist topologies which cannot be compared? All right. Anyway, here, important example, Euclidean topology on the real line. So a set is said to be open if and only if it's the union of open intervals of R or the empty set. Now, I say or the empty set because I'm not thinking about the empty union. Minetti thinks about the empty union. And because he allows for the case of the empty union, he always gets the empty set for free. See how that works? But since I think about unions in terms of sets, and I don't think about the empty union, I usually just say explicitly, I'm including the empty set in my topology, just to be clear, okay? So like, don't waste too much time thinking about that. It's just a matter of, taste, really. Okay, so let's see here. So since the empty set and the whole set are both either by my definition part of the topology, or this is an open interval, and of course any set is a union with itself, right? So certainly we have axiom 1 satisfied, and axiom 2 is true since the arbitrary union of unions is once more a union, right? So if I take a union of open intervals a union of unions of open intervals, I still have a union of open intervals, so it's closed under arbitrary union. The thing that's perhaps a little bit non-trivial is the intersection property. So if I have A is a union of AI and B is a union of BJ, where AI and BJ are open intervals for all I and j indices, then, and of course these don't have to be finite unions, right? These are arbitrary unions of open intervals. Then A intersect B is this intersect that, but then by the distributive law for indexed unions and intersections, we have that this is the union over I and j of the intersection of AI and BJ, but remember AI and BJ are themselves open intervals, right? And if you think about it, the intersection of any two open intervals is either empty or an open interval once more. Now, what do I mean open intervals? I hope I'm not talking past you. There are what are open intervals? There are things of the form, you have things like AB, right? A to infinity, minus infinity to A, right? And minus infinity to infinity. I think, setting aside the empty case, these are open intervals. All right. So if you think about that, either their intersection is empty, right? Or what? Or it's again an open interval, right? So as long as the intersection of these is again an open interval or an empty set, when we take the union, we're still in the topology. So that shows that the Euclidean topology so defined is in fact a topology. All right. Let's see, example 4. Pretty much following Minetti's examples because I think they're good. They're good examples. So this is called the upper topology. So it's the empty set, and again, Minetti does not write the empty set, right? He just uses the empty union to put it in there. But so minus infinity to A, such that A is either a real number or infinity. So that's going to give you that. Those are the open sets in the upper topology for R. Okay. So like axiom 1, it's got the empty set, it's got the whole set, right? Axiom 2, and this is where I was talking about needing the completeness of the rails, I think is right here, essentially. So like if I take the union over minus infinity a sub I, where I is in an index set, my claim is that that is minus infinity to A, where A is the supremum of the upper bounds here. So here I is in I, or it's infinity. So like, let me run through the logic of that. If it's infinity, then it's not bounded above, right? So like if A equals infinity, if infinity is one of these, if there exists an A sub I, which is infinity, then it's the whole real line, right? Otherwise, otherwise it's bounded above. So I think I can pick a supremum of that. I'm trying to think, is that right? Maybe that's not right the way it read. Maybe I should say either this set is, either these are bounded above. I'm not sure my argument's quite tight here. I think there's something missing, but He doesn't really have any details here either. He just claims that this is a topology, but I was trying to run through the axioms for you guys, you know. Does that make sense? Supremum of A sub I, where I is an I. This I is an arbitrary index set. This is a subset of real numbers. So that subset of real numbers is either not bounded above, in which case I think I can argue A is infinity for here, or if it is bounded above, then it is a non-empty subset of real numbers. So by the least upper bound property, it must have the least upper bound, which we call the supremum. And that's what I should put here. I think that makes sense. But anyway, a little bit unsettling, yes. And then axiom 3, well, I take the intersection of these unions over these, you know, minus infinity to A sub I or minus infinity to B sub J sets, and then by the distributive law for indexed unions, I get this. And then I believe what I need then is minus infinity to M, where M is the infimum of these guys, you know. So let's see here, like, or M is equal to infinity. So this set, I guess I can again look at this set. I was more or less thinking by symmetry, but I guess you could, you know, again, hey, I'll let you guys argue in the comments if I'm wrong here. So, sorry. Let us move on. So the infimum is the greatest lower bound of these guys. I think that makes sense. I mean, it's an intersection here. Well, it's a union of intersections, though, right? So unions. So whichever of these intersections is like got the largest AI and BJ should be the one that wins, right? So maybe I'm doing this wrong. Maybe I should say it's the. So M should be like the supreme. I think it should actually be the supremum. Yeah. I don't think that's inf. I think it should be sup again. My apologies, guys. Fix that. I think that should be sup. My bad. Because if I think through it, if I look at all of these guys and I find the... Oh, that's not it either. Oh, goodness. It's the supremum of the... It's the... It may be the supremum of the minimum... I think... Well... Maybe it's this. Supremum of the minimum of AI, BJ. I think I can take minimum of AI and BJ. That's a pair of things, right? So you can take the minimum of a finite set for sure. So this is a finite number. This is a number for each choice of I and J, right? And this is a set of real numbers. I believe that makes sense. So for each index, whichever one of these is smallest is the one which wins in the intersection, right? If this one was -2 and that one was -5, this becomes minus infinity to -5, right? If this one was 5 and this one was 2, this becomes minus infinity to 2. All right, so for each pair ij, the minimum of ai and bj is the one which determines this set. Then you're unioning all those, right? So the supremum of those minimums is what fixes this M, right? It's like the the biggest one of those smallest pairs is what fixes. Oh, okay. I think I just discovered why he doesn't prove it's a topology. I mean, it's not. This should be a Homer problem. Why didn't I make that a Homer problem? I should have made that a Homer problem. I've lost my chance. Oh well. Anyway, so next up, what's a closed set? So you notice that definition of open, definition of closed had nothing directly to do with distance in this lecture. And that continues to be the case. There's no adherence here. It's just pure set theory in the abstract, all right? Now, the specific examples may have something to do with distance and such, but in the abstract, it's set theoretic, right? So X and tau, a topological space, then C, a subset of X, is called closed if its complement is open. And so, easy theorem, the complement of the whole set is the empty set. The complement of the empty set is the whole set, so the empty set and the whole set are closed, right? And by De Morgan's laws, the complement of a arbitrary intersection of closed sets is a arbitrary union of open sets, which is open. So therefore, the arbitrary intersection of closed sets is closed. And likewise, the union of two closed sets is closed. All right. And so you could define topology actually by declaring which sets are closed. Here's an example of that. The cofinite topology. C, a subset of X, is closed if and only if C is either the whole set or C is finite. All right. In that context, the open sets are those which complement C. All right. So like if you're working with an infinite set, right? If X is infinite, then you could think about how that works, right? So in infinite set, if the finite sets are closed, that means that the open sets must be infinite subsets, right? Okay, well, enough about that. Oftentimes, we try to describe a topology not in terms of the axioms necessarily, but in terms of kind of that we have a process of generating a topology through a basis. Okay, so a topological space X with tau has basis B if B is a subset of the topology, and every non-empty A in the topology can be expressed as a union of sets in the basis. And again, he doesn't put not equal to the empty set because he allows the union to be the empty union. All right. Okay, so for example 3, the set of all open intervals formed a basis for the Euclidean topology, right? Because the definition actually was a set is open if it's the arbitrary union of open intervals, right? And likewise, the basis minus infinity to A for A, either real or infinity, formed a basis for the upper topology discussed in example 4. Now, all right, so here's a theorem that tells us how the concept of a basis relates to the definition of topology. So here it is. Let X be a set and B a subset of the power set of X. Okay, there exists a topology on X for which B is a basis if and only if the following two conditions hold. Number 1, the union over the sets in the basis covers the whole space. And also, for any pair in the basis and any point in the intersection, there exists another element of the basis which is contained in the intersection of the basis sets. All right, like in this picture. A, B, X, then C is in the middle, like that, yeah. So to understand this theorem, it's saying that if you have a subset of the power set, all right, and conditions 1 and 2 hold for that set, then it is possible to define a topology, right, for which the set B is a basis, all right? And that process of defining a topology for which B is a basis is called the topology generated by B, all right? Again, example 3 is an example. And example 4 is an example of topologies generated by a basis. And our proof that we're about to go through is going to have to go through the same ideas, essentially. All right, so forward implication. So I'm going to assume that a topology, it's too late to topologize. X has already been topologized. There exists a topology on X for which B is a basis. Now we need to see that these two conditions hold, all right? So the first one's pretty easy. Since X is an element of the topology, it follows that there exists a collection of sets in B whose union is X. Then if we take the union over all B in B, we must likewise produce X. I think that's somewhat clear. Now, since A union A is A, we have that A in the basis means that A is the union of it with itself, right? Which means it's in the topology. So A is in the topology. And likewise, if B is in the basis, B is in the topology. Which means then, since we're assuming that it is a topology, right? It's too late to topologize. It's already topologized. A intersect B is in the topology. All right, but that's not what I need, right? I need that for each X in AB, I need to find a C, which is inside A intersect B, right? So here we go. I'm trying to prove 2 right now. So am I off? Hopefully I'm not off the screen. All right, so yeah, I'm not off the screen yet. Yeah. All right, so if X is in A intersect B, well, this is in the topology, right? That means that there's a union of basis elements, basis sets rather, which is equal to A intersect B. But if X is in this union, that means that there exists an index I naught in I for which X is an element of B I naught. And so we can just set C equal to that basis set, and that will be a subset of A intersect B with C in the basis, and therefore 1 and 2 hold true. Hooray, that's half of it. That's the half which Minetti doesn't bother to prove. He just says it's clear. And he's probably right. Proof continued. All right, so suppose X is a set, and we have a subset of the power set of X for which 1 and 2 hold true. I'll remind you that means that the union over the set gives you the whole space, and for any pair and any point in the intersection of that pair, there exists a third basis element, set, for which X is contained in said set, which is a subset of the intersection. Okay, we want to show that B is a basis for topology X, topology tau on X. My claim is that we may define a topology tau on X by generating its open sets as unions of sets in B and the empty set, all right? Or if you're Minetti, you just say unions of sets in B because your concept of union includes the empty union. All right, so axiom 1, clearly both the empty set and the whole set are in the topology since they're formed by unions of sets in B by 1. And phi is an element of the topology by my definition. At this point, I realized Minetti cites empty union, which I forget at times. All right. Axiom 2. All right, so axiom 2 here, if we have AI is in the topology for I in I, then that means that there exists a J sub I in J sub I for which A sub I is equal to the union over J sub I and big J sub I of B J sub I, where B J sub I is in the basis. Oh. In other words, I'm saying that if you have an element of this topology, it has to be a union of things in the basis, all right? And so if I have an arbitrary union of such things, then it's an arbitrary union of this arbitrary union, right? But an arbitrary union of an arbitrary union is, guess what? An arbitrary union. So it's still a union, which means that it's in the topology by definition. Hooray! So that's axiom 2. Axiom 3 requires a little bit more trouble, but here it is. If A and B are in the topology, that means that they can be expressed as unions over the basis, right? And therefore the intersection by the distributive law is the union over the intersections of the basis. But the intersection of the basis elements can be written as the union over C, such that C is an element of the basis and C is a subset of BI intersect BJ. This is true by assumption too. And that's probably about a homework problem worth of work. There's a little gap right here. But that rather natural statement accepted, we have then that A intersect B is an element of the topology so defined because it was formed by the union of basis elements. And there you go. That's theorem 3.7, which gives us license to define a topology, right, by a subset of the power set which satisfies these two conditions, if we like, right? So, in contrast, if the topology is already given, right, then we don't have to check these two things. We just need to, if the topology is already defined, then a basis is simply a collection of open sets whose unions form everything in the topology. So, let's see here. 6. The lower limit line. Now, I will tell you, when I was a graduate student, or undergraduate, I can't remember, whenever I took topology the first time, I think I was a graduate student. Goodness, I can't remember. Anyway, yeah, I think I was a graduate student. When I took the topology, we had a homework problem on this, and this stupid thing threw me for a loop. It's just very non-intuitive, this lower limit line. But anyway, so the lower limit line is defined by, it's the topology for the real line, which is generated by the basis containing these half closed, half open in the usual vernacular intervals, right? So, of course, in the lower limit topology, this is an open set, all right? And, but you know what? Open intervals are actually the union of all of these half-closed in the usual vernacular sets, intervals. And so that means that this A comma B is open in the lower limit topology, which is to say that the open set from open interval from A to B is in the lower limit topology. But of course, you can prove that the, interval from A to B with B excluded, A included is not a open set in the Euclidean topology. And in fact, we can argue that the lower limit topology is a finer topology than the Euclidean topology, and our Euclidean topology is a coarser topology than the lower limit topology. All right, and if you look at the footnote on page 41 of Minetti, he mentions that this lower limit line, it's not just a thing invented to torture topology students in homework. It's actually something that someone used in solving a concrete applied problem that was somewhat difficult. All right, so example 8 is on the disjoint union, which I just want to say a word about. Disjoint union what it's saying is it's not a union in the sense of the usual sense of the word, because the disjoint union of R and R is not just R again, right? So I would say disjoint union is more like a Cartesian product, all right? Anyway, you can look up specific set theoretic constructions for disjoint union if you're curious. They do exist. And if you can't find it and you're interested, just ask me. I'll find it eventually. Anyway, so if we have topological spaces, a collection of them x sub I for I in some index set, then we can form the disjoint union of all of those guys, and that can be given a topology. In fact, this is the most coarse topology possible to give to this disjoint union. And it's just simply this. A subset of the disjoint union is open if and only if the intersection of A with x sub I is open for all I and I. So that's kind of a neat little example. But Anyway, so I would point you ahead to section 3.4 on metric spaces. This will bring many further examples which you might find familiar. The point of this section is not to really make you comfortable or to show you things you're familiar with. It's more to illustrate the quirks and features of the definition of topology, and in fact, what follows next is really quite divorced from the usual. But it's a fascinating and important example, especially for those of you who are interested in algebraic geometry. So this is what's called the Zariski topology. And the Zariski topology is this. So if we have K a field, and we look at the ring of polynomials in n variables, then for f a polynomial in n variables, we can define the df, which is basically the subset of kn on which the polynomial is non-zero. And since if you look at the zero polynomial, well, everything's zero for the zero polynomial, so that means the d of 0 is the empty set. On the other hand, if you look at 1, then d of 1 is just the constant function 1, right? So like it's always non-zero for everything, so its d is just kn. So we have the empty set, the whole set, and if you want to intersect two of these guys, you can just look at the product of the d for these two. And so we can use df, the set of such df's, to generate a topology on kn, which is called the Zariski topology. And you can define the complement of df by vf. This is the zero set of f, all right? And if we had E is some collection of a subset of Kn, all right? Sorry, got lost all of a sudden. Why would F be an element of E? I thought F was a... I thought F was a polynomial. Why would it be an E? It doesn't seem right to me. Uno momento. Let me check on this. I may have written something dumb. Oh, E is not a subset of Kn. E is a subset of duh. Sorry, guys. There's just a... There we go. That's better. So E is a collection of multivariate polynomials, right? And so VE is the intersection of all of the zero sets for the polynomials that are in E. All right. And anyway, you can argue that VE are the only closed sets in the Zariski topology. And then he proceeds to give this argument in orange, which I believe intends to prove this claim. But I'm reluctant to hold your feet to the fire on this because it requires, I think, abstract algebra 2, and so I'm not requiring that as a prereq for this course. I will say this: if you want to understand the orange stuff here, then it would be wise to pick up the copy of Dummett and Foote that you have and look in the chapter on, I think there's a chapter on algebraic geometry in there, and there you'll find a more complete discussion of the Zariski topology and the theory of ideals and all this that's needed to sort through all these things properly. I'll just, let me just give an example here. So, what example am I on? Example 9, I guess. So just to be, example 10. So if we're looking at, say, k equal to the reals, right? And we could look at, say, f of xyz equal to, it could be any polynomial, but we could do like x squared plus y squared plus z squared, I don't know, minus 1, right? All right, so then the df would be what? It would be xyz such that x squared plus y squared plus z squared minus 1 is not equal to 0, right? And that is, something in the basis for the Zariski topology, right? On R. Well, here, well, the Zariski topology, so we're looking at the Zariski topology on R3, okay? So here is a particular basis element of the Zariski topology on R3. What is this? This is what it is, right? And okay, so what's the complement of this? Maybe I write it this way: x squared plus y squared plus z squared equal to 1, right? So this is what? This is, what is it? Just the unit sphere, right? So the unit sphere is closed in VF, right? Because it's the complement, VF, listen to me, in the Zariski topology, right? Because it's the complement of what? Of the open set DF, right? So it's kind of mind-bending, but think about it for a second here. The open set, one of the open sets in the Zariski topology is everything that is either inside or outside of the unit sphere, right? Of course, you could also take polynomials that are like x plus y plus z minus 1, right? That would be, or just x plus y plus z, that would give you the plane with normal 1, 1, 1, right? That's a closed set in the Zariski topology, but its complement is open in R3. So the Zariski topology is interesting, but if I recall correctly, it has properties which are rather different than typical metric topologies. So perhaps we'll come back to it as the course goes on. I think it's important to mention because I know some of you are interested in going on and studying algebraic geometry more, and this is, kind of the start of that. So, two different ways to look at spaces. The one is, I would say, manifold theory, which tends to be essentially the parametric viewpoint, right? We have an abstract space. We talk about charts from open subsets of Rn into the space, right? And we study how these charts interrelate. This is the manifold description of a space. In contrast, the algebraic geometry way of describing a space is as solution sets of like polynomial equations or something. So it's more, and you see this in calculus 3 as well, right? So in calculus 3, we describe surfaces either as like the level set of a function of 3 variables, or on the other hand, we describe it in terms of a patch, right? X of uv. So the patch is really the manifold kind of perspective, whereas the level set is more the algebraic geometry perspective. And I'm less well versed in the algebraic geometry perspective, but these are two, competing viewpoints to describe spaces and their geometry, and they both have their advantages. But anyway, this is interesting because this is the topology, which is natural in some sense for the algebraic geometry way of thinking about things. And you notice that this was for a field. It didn't say that that field had to be reals or complexes. These things, if I understand correctly, are good even over the sorts of fields that number theorists care more about. So there start to be interesting connections between, say, algebraic geometry over finite fields and, the kind of number theory I don't know. But anyway, hey, that's it for this time. So thanks, guys.